about if you have a vector, suppose we have some space or space-time within us. Let's say we have space-time and let some x be a point in the space-time. Let x be a point in the space-time. Then we can define a vector A at this point x, that is vector A at x. X can be a position in three-dimensional space or an event in four-dimensional space-time. Then set of all such vectors x fixed will form a vector space which we can call it as Vx. Is a vector space. And this vector space is different at different points. Okay? You can also have set of all one forms that are defined. This is dual space at x. So at every point in the space, you can define a vector space and its dual. So that all that we have discussed can be defined at a point in the space. Now you change the point, then you get what is called a field. If you define vector at different points, it becomes a vector field. If you change scalar at different points, it becomes a scalar field. If you change tensor at different points, you get a tensor field. Okay? So, now if you define the set of all VL, we get what is called a vector field or a tensor field and things like that. So everything that we discussed in the last 1 hour, 1.5 hours can be done at every point. You can define a vector space, you can define a dual vector space, you can talk about tensors, you can talk about tensors of any rank, but they are all at some point. Now you can have at another point a different vector space, tensor space, etc. So everything can be now made a function of the point. So you get what is called, so you have different vector spaces. Yeah.
But x is in the tilde is subscript or superscript?
Essentially, when I say ax, it is not an index. This x is not an index. It is simply to say that this a is at x. Okay? So, a little bit more cumbersome if I write that also, because we are already writing a lot of pieces. So let's understand, I am not going to amplify on this, but this concept is a little bit important concept for one reason. That's why I am introducing this. After I introduce that, I will not write about this field again. So maybe towards the end of today's lecture, maybe I will come back to it again. Now, why this space is important is because you can define what is called a coordinate system. You have a point, and then you can have a coordinate system, having coordinates x1, x2, x3. Then you can define what is called a displacement vector. Okay? So that means if you have a point here and this can be written. Let us imagine in 3 dimensions. To start with, let's say I can write a coordinate system. So let's say this is x1 and this is x2 and this is x3. At this point x, now after some time, I can choose a coordinate basis. Coordinate basis is a special basis. Coordinate basis is a special basis in the sense that the basis vectors are along the direction in which x1 increases, x2 increases, and x3 increases. Okay, so E1 let me put this x is the direction along which the coordinate so generally let me put it as Ejx coordinate xj increases at x. So I am going to choose this is not any arbitrary basis. Coordinate basis is a fixed basis. At every point we can define a coordinate basis. Okay, depending on the dynamics of the particle, you can define a displacement. The displacement vector can be resolved into components along x1, y1, x1, x2, and x3. So that is called coordinate basis. Do you understand now? Coordinate basis is a very specific basis. Coordinate basis is the direction in which the coordinates increase at every point. Now you can say that the particle may be taking a curve with trajectory like this. So these directions will be different at different points. So they are actually moving coordinates. At every point they will be different. Correct? So it is connected to the point in which you are defining your vector space. So this basis, so Ejx is the basis for the vector space defined Bx. At every point you can define a vector space, and coordinate basis is the basis for that vector space. Okay, so that you can write down the displacement dx. The displacement vector dx can be written as dx alpha into E alpha x. If I choose this as the coordinate basis, then the displacement vector can be written as dx alpha into alpha x. This is the displacement vector. Yeah, we will come to that. So let me first tell you that you can, what is called the displacement vector is this, then you can define ds squared as dx dot dx, which is simply dx1 squared plus dx2 squared plus dx3 squared. Okay. Now, if I make a change of basis, that is, you can always choose another basis, right? the change of basis is always associated with a linear transformation. Correct? Suppose if I go from E alpha x to some other E prime of alpha x, some other basis. Okay, so let me suppress x. So E alpha will go to E alpha prime. Then we can always write this E alpha prime as some kind of L alpha beta into E beta, sum over beta. I am writing this explicitly because this L alpha beta is not a tensor. It is simply a transformation matrix. So I am writing summation explicitly. You can write down transformation matrix from L alpha beta to E beta. One particular example of a transformation is rotation. Suppose you rotate your coordinate system, your basis will be different. The rotation matrix will transform the basis vectors from one basis to the other basis. On the other hand, you can choose any 3 by 3 matrix to be a transformation of the basis. You will get some basis. Correct? So, now if you have another basis, E alpha prime, and if you have E beta, then what is the way in which your coordinates are transformed? How are these coordinates transformed? For example, you may say that your dx vector will be written as dx alpha into E alpha. Equivalently, you can say that it can be written as dx prime beta into E beta prime. You can say that it can be written as dx prime beta into E beta prime. The coefficients outside, the components will be different in different bases, but the vector will be same. So if we have a different components, the components can be also related to each other. So how do we do that? Now, you can say that in this case, so dx prime of beta into E prime beta can be written as dx prime of beta into E beta. I can write it as sum over some gamma into L beta gamma into E gamma. L beta gamma into E gamma. So gamma is summed over.
Could you repeat that part?
Yeah.
Could you please repeat that part? Could you please repeat what?
So I have written it in this way. Okay. Or maybe let me put it slightly different. So let me use it. So this is in terms of the old basis. I can also write this in terms of the new basis as dx prime alpha E alpha prime. Okay, this is the new basis, this is the old basis. Now if E alpha prime is related like this, then E alpha can also be related with sum over beta to this L inverse of alpha beta times E beta prime. Correct? So I can get the inverse of this and then get it like this. So supposing if I start with that, this is already remember that this dx prime can be written as sum over alpha. Let me first for the time being write this dx alpha e alpha, which is nothing but sum over alpha dx alpha into sum over beta L inverse of alpha beta into E prime of beta. So this is equal to, let me write this sum over beta outside and write this as sum over alpha dx alpha into L inverse of alpha beta into E prime of beta. Now if you look at this one, compare this equation with this equation. So if I write this as beta, beta just for, beta is dummy anyway. This is nothing but sum over beta dx prime beta into E prime beta. So whatever is this bracketed quantity is the dx prime. So dx prime, so alpha is summed over here, so we get dx prime beta is equal to sum over alpha dx alpha L inverse of alpha beta. So if E alpha is going to if E beta is going to E alpha through L matrix, dx alpha will go into dx prime alpha through L inverse matrix. So that is the components will get transformed to the inverse of the matrix that transforms the basis vectors. In rotation cases, this is very simple. In rotation case, you will have an orthogonal transformation, which means the inverse is same as the transpose of the matrix. In three-dimensional rotations, you will have this matrix to be an orthogonal matrix. The transpose is the inverse of the matrix. So it is very easy to see it in the rotational case.